In this video, we're going to talk about how to process images such that you can extract different objects from them based on their color. So we've talked before about how to represent images, where images are really just three-dimensional matrices, a dimension for width, a dimension for height, and a dimension for color. And typically this color dimension has three different components in it, a red component, a green component, and a blue component. You might ask, why these three components? Well, it turns out the human eye has several different types of cells inside of it that can respond to the light around you, as rods, which are really good at detecting the intensity of the light around you, and cone cells, which are really responsive to different types of colors. And you have three different types of cone cells in your eyes. One, as you can see on the graph here, is responsive to the blue type of color of light. One is more responsive to green, and one more responsive to red. And in this way, we can take those red, green, and blue values and represent any color that the human eye can see. So the natural first type of color camera created had a red component, a green component, and a blue component in it to recreate images for the human eyes. So let's try this out for the purposes of robotics. Let's take this example. How do we extract only the pixels that match one color in an image? Well, we go through the image and we threshold based on the RGB value of each pixel. So we go through pixel by pixel and say, is this red enough, green enough, and blue enough to match the threshold that we're looking for, and give an output for that. And it turns out there's a really nice OpenCV function for this called InRange. InRange takes in your input image, takes in a lower bound, which is in whatever color type your image you're giving it. So in this case, it's a blue, green, red tuple. So blue component, comma, green component, comma, red component. And then an upper bound, which is the maximum of that color value in the same format that you want to accept. So the maximum amount of red, the maximum amount of green, the maximum amount of blue. And this goes and gets put into an output image at the end. And this basically produces a binary image. Either the color was present or it was not. So if the color in that particular pixel was in the range you specified, the output pixel will be white. If not, it'll be black. So let's try this out. Try to find all the red pixels in this picture on the left here. So this will primarily be the pixels for that little ribbon on the right-hand side of the image. Let's use the InRange function. And let's say we don't want anything from the blue component, so the maximum and minimum that we're looking for is 0. We don't want anything from the green component, so 0 is on both of that. We want to get all of the red components, so if it has any red component but not blue or green component, we want to get the output of that. What does this give us? Well, it certainly doesn't give us the ribbon. In fact, it gives us some kind of odd pixels here and there, but nothing really discernible. Why is this? Well, even though the ribbon looks really red to us, it probably has quite a bit of blue and green in it. So let's try again. Let's specify that we can allow a little bit of blue, a little bit of green, and then our 0 to 255 of red. What does this give us? Well, we can get the ribbon for sure, but we also get quite a few black spots. This is because 50, 50, 50 would look pretty black to us, very dark, shadowy, but it also responds to this filter, and that's definitely not red. So how do we do this? Well, let's start by rethinking how we represent color in the image. So what if we represent color using a number to represent the distance from white in the pixel? So this would be called saturation typically. A number to represent the distance from black, which is typically called value. And note that you could put white and black on the same axis, two parts of the same axis, but then what do you do with all the colors in between? So instead we're just going to pull out all the black and all the white separately. And then what's left is what we typically call hue. So the number that remains is called hue. And this produces an interesting different type of color space. On the bottom right here you can see the color space here where we have saturation going from pure white in the middle to whatever color it is we're looking at towards the edge of this cylinder. We have value, which goes pure black on the bottom to whatever color we're looking at up on the top of the cylinder. And then we have hue, which goes around on the color wheel 360 degrees around and has every color of the rainbow, so every color we can make that the human eye can see. And this is called HSV space, and it's very useful for us when we're doing color filtering because now we can look for just one value. So we can set saturation and value to some reasonable number, and we can decide which range of hues to look for, so we find whatever color we're looking for, so red for example. And just to note, there's another type of space called hue saturation lightness, which is very similar to hue saturation value. It's not used quite as much, but you may come across it at some point, so I wanted to make sure you could see that the cylinder on the left here is pretty similar. It goes from solid black on the bottom to solid white on the top, where the full value of the hue is towards the outside of the cylinder. So how do we get into this color space? Well, there's an OpenCV function called convertColor, where we take in our input image, tell it how we want the conversion to be performed. So in this case, we're going from the OpenCV standard BGR to HSV, and it goes into this output image here. And just to note, there are a number of other types of conversions you can do here. You can do HSV to back to BGR, you can do BGR to grayscale, and there's a number of other types as well, but these are the ones we're probably going to be using for the rest of the semester. So let's try this out with our original image. Let's try to find all the red pixels again. So we're going to first convert color into HSV space, and then we're going to use the same InRange function on the HSV image because now it's a different type of space. And in the first component, we're going to only look between 170 and 180. So first a note on hues in OpenCV. In an 8-bit image in OpenCV, which is what we're going to be using, the hues range from 0 to 180. This is because it's a circle, so 360 is natural, but 360 doesn't fit into 255 bits, so they divided it by 2 and made it 180. And if you play around with the numbers a little bit, you'll see that red is towards the top of that, so towards 180, and it wraps around the other side a little bit on the 0 side. And through a little bit of trial and error, I found that 170 to 180 did a pretty good job of finding this red ribbon on the right-hand side. So I chose that. Now the saturation, we want to be towards the higher end of the saturation because higher means more of the color we're looking for, but we don't want to throw out everything that's not purely red. So I chose 100 to 255, that seemed to work okay. On value, we can be a little bit more flexible because a lot of the red here is sort of in shadow, so it looks a little bit darker to the camera than it does to our human eye. So I said 20 to 255, and again, it worked out okay. These are just things you can experiment with to find good values when you're trying to actually find something in an image. So what's the output of this? Well, we see a pretty good view of the ribbon here. We see a few other pixels, but they're not such a big deal. In fact, next video we're going to talk about how we might remove those things, but for now we're just going to ignore them because we got a pretty good image of the ribbon here. So we can move on. So what does this image of the ribbon here really show us? Well, it's a binary image, it's off and on, and it tells us which of those pixels in the original image are the ones we were looking for. So wouldn't it be nice if we could color those in, so that maybe if we have multiple different filters stacked on top of each other, we'd be able to see which part of the filters were responsive to the red, which part maybe to white or yellow or blue or anything else we're looking for. So we can do that with OpenCV using mass. And to start with, we're going to talk about how to do bitwise operations. So OpenCV has a number of different functions for how to do bitwise operations on images. And this is where you take in a first input image and a second input image and do some logical operation on them. In this case, we're going to talk about the AND operation. So we'd be saying that from image 1 and image 2, if the same pixel is on both of them, then the output will be on. If only one of them is on, or neither of them are on, then the output will be off. So just a logical AND operation here. And we're going to give one more parameter here, and this is the mask parameter. And this is nice because you can give a binary image to the mask parameter and use a color image on the input on the left-hand side here for image 1 or image 2, and end up only showing the values that were in the mask. So only ones were activated by the mask, which is the output from your filtering step. We're going to do an example on this in a second to make it a little bit more clear. And this, of course, becomes the ANDed image in the end as the output. Just as a note, there's also a bitwise OR, where you can take in image 1, image 2, and a mask still, and it just does a logical OR. So if either the pixel on image 1 or the same pixel on image 2 are activated, it will be activated in an output image. So let's do an example with this. Let's say we want to filter that same input image for red pixels. We've already done that. We've seen what that looks like. Let's say we want to filter it for blue pixels after that. That seems pretty straightforward now that we've figured out how to do it with red. Just change the hue values around. We're going to bitwise OR both of those outputs, so the filtered red and the filtered blue. We're going to add those two together, and then we're going to combine that with the input image so that we get an image that's either black, blue, or red. Nothing else. So let's try this out. First we filter red, which we've already seen the output image for. Then we filter for blue. And you may not even have noticed there was any blue in this image to start with, but there's just a little bit of blue around her tag right here that we can pick up, and that shows really nicely in the output image there. We're going to add those two filtered images together so that we end up with a filter on the right here, which is all of the blue and all of the red in one image. And then we're going to combine that with our original input image so that we can see an image here that's only black, blue, or red. So we've done it. Great. And here's the OpenCV code that generates all of that so you can use it later on when you're doing your homework assignments. So first we convert our color image from BGR to HSV. And then we do the InRange function for red, which again I found that the hue values 170 to 180 were pretty good for this type of red. They may vary just a little bit. You may need to do this twice, where you do the upper end of red, which is roughly 170 to 180, and then the lower end of red, which is maybe 0 to 10, 0 to 20, depending on exactly what type of red you're looking for. But we now know how to bitwise OR those together, so you can end up with one image for it. And then we do the same sort of in range on blue here. We look at the hue values from 110 to 130, and I left the saturation and value parts the same. Seems to work just fine. We make a combined mask of that using bitwise OR. So if either OR, blue or red, was activated, we had activated it in the end. And we did a bitwise AND operation using the mask parameter here to create our final image, where we essentially colored it. One thing to note, typically when you just want to mask an image, when you're not really trying to bitwise AND anything, people tend to use bitwise AND, and you give the input image as both image parameters coming in, because if you think about it, that means that you will get the exact same image out, and then you just apply the mask at the end. This seems to be the standard the community has decided on, so we'll do that through this class, but feel free to experiment if you want. So how does this help us find lanes? This is basically step one towards finding lanes. First, we need to get rid of everything in the image that's not the color of the lane, because Duckytown is nice enough that we can see that there are just white things, yellow things, and red things. So first off, we're going to want to take our input image here, which you should recognize from homework 8, and we're going to want to find only the white things in it. So we see these lanes pretty prominently here, the white on the right, the white on the left. There's also a lot of garbage in the background that you probably already got rid of in homework 8, but we can see the lanes pretty well, and that's what we're going for. And this is with just the filtering step, just that in-range step, although not looking so much for hue on this part as for looking at saturation and maybe value, but that's for you to play with in homework 9. And then we also want to do this with the yellow lines in the middle. So this is the output from the yellow lines that you should be getting at in your homework. And this is just the filtering step, so we don't yet know what pixel values any of these are at, we don't yet know what type of a line they make, we don't know any of these things, but it's the first step. So let's review. First, we talk about color spaces and why hue, saturation, and value is a good way to represent color in an image. Then we talked about how to filter color using OpenCV. And finally, we talked about how to do a masking step, which really just makes it more helpful to debug the image at the end. And this will get you your first step towards building your own lane filter.